Now let's do some exercises. We'll start out with a little bit of concept review. Think about the force on a charge that's just sitting still in this magnetic field. What kind of force would it experience? If you said none, that's right. Now let's look at three possible scenarios. This charge could move in this direction, we'll call that 1, in a direction like this, 2, and in this direction, 3. In which direction would this particle feel the most force? If you said direction 1, that's exactly right, because the magnetic force is proportional to the perpendicular component of the velocity of the particle. So will any of these directions cause zero force? If you pick direction 3, that's exactly right, because direction 3 has no component perpendicular to the magnetic field. Now let's do some math. Let's say you've got a particle of charge Q is plus 1 coulomb moving through at a velocity v equals 1 meter per second in a magnetic field with a strength of 2 Tesla. Can you calculate the vector force acting on this particle? Why don't you pause the video and do some math? Now let's work through this together. We know that the force is equal to QVB sine theta, but in this case, all of V is perpendicular to the magnetic field, so we don't have to worry about the sine theta term. So we just end up with that the magnitude of the force is equal to the charge, 1 coulomb, times the velocity, 1 meter per second, times the strength of magnetic field, 2 Tesla, which is just 2 newtons. Remember that newtons is the unit for force. This is an SI unit. Now let's think about the direction. You'll have to use the right-hand rule here. You should have found that the direction of this force was into the page, like this. Let's try something a little different. Can you find the force on a segment of wire of length L equals 2 meters with current flowing through it of 1 ampere if it's sitting in a magnetic field with strength 3 Tesla? Let's give this a shot. Force is equal to ILB sine of theta. I made this problem really simple by making sure that I was perpendicular to B, so we don't have to worry about sine theta. But it's always good to remember that sine theta is a factor. So I was 1 ampere times 2 meters times 3 Tesla. We end up with 6 newtons. And by the right-hand rule, we can calculate the direction. You'll find that the direction is perpendicular to both I and B, and it's out of the page. Let's work one last problem. Let's say I put a wire loop into a magnetic field of strength B equals 2 Tesla. Let's say that the length here, B, is 2 meters, and the height of the loop is 1 meter. Can you calculate the magnetic force acting on this part of the loop and this part of the loop, the length and the width, if the current is equal to 2 amperes? Remember to specify the direction. Let's try this out. First, let's think about this conceptually. The length of the wire is parallel to the magnetic field, so this part will experience no force. The height of the wire, however, this part here, is exactly perpendicular to the magnetic field, so we know that the force is going to be equal to ILB. We don't have to worry about sine theta because it's exactly perpendicular. ILB in this case is going to be 2 amperes times 1 meter times 2 Tesla, so we get 4 newtons. Just like in the last problem, the force will point out of the page. Great job!